Hello, class. So on this video, we're still on section 6.2. In the previous video, we talked about, and videos, we talked about the Laplace inverse, right? And how to use the linearity property to simplify problems, right? So how to find the Laplace inverse of certain things. Right? So we did that in example 7. The last thing we have to talk about is how to find the transforms of derivatives. What's the Laplace transform of a derivative? Well, this is how we're going to do it. We're just going to plug the derivative right into the formula and see what happens. Right? First, suppose that you have a function whose derivative, f prime of t, is continuous for t greater than or equal to 0. What we're going to do is we're going to use integration by parts to simplify the Laplace transform. Okay? So by definition, the Laplace transform of f prime of t is going to be equal to limit as b approaches infinity, right, of the integral from 0 to b of e to the negative st times f prime of t dt. Right. Now we're going to use integration by parts. So by integration by parts, we're going to let u be, oops, that looks like a weird u. We're going to let u be equal to e to the negative st, which implies du is negative s e to the negative st dt, and then we're going to let dv be equal to f prime of t dt, which implies v is just f of t. Okay, so by integration by parts, we can write this integral. This is going to be, and let me choose a different color. By definition, this is going to be, I think I might need more space. It's going to be equal to the limit as b approaches infinity. And again, we can just worry about the limit later. Right? It's going to be uv, right? So e to the negative st times f of t, evaluated from 0 to b, minus the integral of v du, right? From 0 to b of v du. V is f of t, du is, we'll put it in front, negative s, e to the negative st, dt. Now, I'm going to simplify some things on the inside. So let's plug in 0 and b. Right. So let's use a different color. Let's make it more colorful. Let's use orange. Right. So e to the negative st times f of t evaluated from 0 to b. Let's plug in b first. Times f of b minus e to the negative s times 0, right? That's e to the 0, which is 1. F of f, replace t with 0, so this is just f of 0. Now, plus, because we have minus minus, right? So minus minus is plus. S is a constant for the purpose of the integration, so you can move the s outside. Integral from 0 to b of e to the negative st f of t dt. Now, it would be nice, because now we're just going to evaluate the limit, it would be nice if this thing were going to 0. That would be very nice, right? Because that would simplify things a lot. But if, in order for that to go to 0, right, because what we're saying is that we want the limit as b approaches infinity of e to the negative sb times f of b to be equal to 0. Right? Well, if s is greater than 0, okay, so actually let's rewrite this. It's going to be the limit as b approaches infinity of f of b e to the negative sb, right? Now, if we want this to be equal to 0, right, so when this is true, so what's going on? We did an example like this before. We know that the denominator is growing really fast. However, the problem is f of b, right, so f could also be growing very fast as b approaches infinity. So what is the necessity? What is the requirement for this limit to actually go to 0? Well, certainly f of b cannot be growing very fast, right? F can't be growing very fast. Well, we have a condition for that. We have a way of showing that f doesn't grow very fast. In particular, we know how to say that f grows at most as fast as an exponential, a constant times an exponential. And that's precisely saying that f is of exponential order, right? So as long as f is of exponential order, we can guarantee that this actually goes to 0, right? So this limit is 0 if f is of exponential order. And again, the reasoning is because it can't grow too fast. It definitely can't grow faster than an exponential, right? So we restrict the growth rate of f to what? For f to grow at most as fast as a constant times an exponential. That's exactly saying that f is of exponential order. Okay, so if we assume that f is of exponential order, right, and that s is greater than 0, right, so we're assuming that s is greater than 0, then what do we get? Well, this part goes to 0, like we said. So we're left with, now this is a constant, so limit of that is just itself, right? So we get negative f of 0 plus, right, s is a constant for the purpose of the limit because the limit is in terms of b. So we get s times the limit as b approaches infinity of the integral from 0 to b of e to the negative st f of t dt. And this, by definition, is the Laplace transform of f. Right. So this simplifies to negative f of 0 equals s, plus, so this whole thing equals negative f of 0 plus s times the Laplace transform of f. And this Laplace transform, we know it exists. Why? Because f is continuous, right? So it's piecewise continuous. And it's of exponential order, right? So both assumptions, one assumption that we made at the start, f being continuous, another assumption f prime being continuous, right? And another assumption that we made at the end, that f is of exponential order, right? So I guess here, f has to be piecewise continuous, at least. Right? As long as that holds, f is piecewise continuous. Its derivative is continuous for t greater than or equal to 0, and f is of exponential order. Then we have this really nice formula for the Laplace transform of the derivative. We can write it in terms of the Laplace transform of the original function. Let me make that more readable. Look, that looks like an integral sign, not like an S. Right. And that's the idea. We can actually do this for higher order derivatives under the correct conditions. Right? And this is the theorem that we're going to use. So theorem 7. If f prime up to f to the nth minus 1 derivative are continuous on 0 to infinity and are all of exponential order, right? And if f of n, so the nth derivative of n, is piecewise continuous on 0 infinity, then what do we get? We get this formula. The Laplace transform of the nth derivative of f with respect to t is given by the Laplace transform of f. Right? And it has this really nice formula. So s to the n times f of s minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime of 0 minus minus f to the nth minus 1. And again, this is derivatives, right? Evaluated at 0. Right? So a really nice formula. Again, we only need to satisfy these conditions, right? That f prime up to the nth minus 1 derivative are continuous on 0 to infinity and are all of exponential order, and that the nth derivative of f is piecewise continuous on 0 to infinity. And I think that somehow guarantees the existence of the Laplace transform of f. It's something that we would have to prove, that if this is piecewise continuous, or that, oh, I'm already assuming that f is continuous. Okay, so we're fine. Right. Okay, so we're good. So we're assuming f is continuous. So these are really all the assumptions we need. Right. So I was going to say, like in the previous example, I didn't assume that f was continuous, only that its derivative is. right? So at the end, we had to say, well, f has to be at least piecewise continuous. So here we are saying from the start, let f be continuous. So we don't have to worry about any of that. So a very nice theorem. Now notice that as long as we know the Laplace transform of f and f itself, we can calculate this, because what are the constants going on? So f of s is the Laplace transform of f, which we can find if we know what f is, and assuming that the Laplace transform exists, and we have a formula. S to the n, well, that's just some polynomial in s, right? And f of 0, f prime of 0, all the way to f to the nth minus 1 derivative of 0, if we know what f is, we can find all of these derivatives, and we can evaluate them at 0. So basically, we know what every term in this formula is. Let's do a quick example. Use the Laplace transform to solve the initial value problem. dy dt plus 6y equals e to the 4t with the initial condition y of 0 equals 2. As I mentioned before, we're done with all the pieces that we need. We needed to define the Laplace transform, we needed to define the Laplace inverse, and we needed to find a formula to calculate the Laplace transform of the derivative of a function, or higher order derivatives. So let's try to apply this here. I already gave you a hint of what to do. Right? I mentioned that in previous videos. I mentioned that what you want to do is take the Laplace transform of both sides of the ODE. Right? So let's start with that. Let's take the Laplace transform of y prime plus 6y, and this has to be equal to the Laplace transform of e to the 4t. Now we have a formula for the Laplace transform of e to the 4t. Let's go to our theorem. This is going to be 1 over s minus 4, because a is 4. Okay? So the right-hand side is 1 over s minus 4. For the left-hand side, we have to simplify a little bit. It's to the Laplace transform of y prime, so we can separate the sums, plus 6 and move the constants outside, plus transform of y. Now, since we're assuming that the derivative of y exists, right, that also means that y is continuous, right? So as long as this derivative has, or that our function is differentiable on 0 to infinity, right, then we know that the function, or any solution, is going to be continuous on 0 to infinity, so the Laplace transform exists, assuming that, the function is at most of exponential order. Now, you could use theorem 1, right? This is first order linear. So you could use theorem 1 from section 2.4 to actually verify that a solution exists for this differential equation from negative infinity to infinity, right? That's an exact interval at which the solution exists, meaning that the solution is differentiable, because we have to take its derivative, meaning that it is continuous on negative infinity to infinity, meaning that it is continuous on 0 to infinity. So let me make a note of that. By theorem 1, section 2.4, a solution y of t exists on negative infinity to infinity, which implies, for our purposes, that y is continuous on 0 to infinity. So as long as the function, its derivatives are of exponential order, this is justified. Now, although we don't know what y is, all we can do is first do the work, right? And if it works, right, so if we find a y and y is of exponential order, then this work is justified, right? So it's kind of like doing the work first and then verifying that every step is justified based on the solution that we got. But at least from the start, we can say that y is at least, whatever solution we get, is continuous on 0 to infinity. Okay, now let's use formulas. We know what the Laplace transform of y prime is, because we have a formula for that. That's, okay, so n equals 1. So when n equals 1, so let me write a couple of these terms, right? So you know how to use the formula. So when n equals 1, we get s times f of s minus s to the 0, right? N minus 1, when n is 1 is 0. So s to the 0 is 1, f of 0, right? When n is 2, we get s squared, f of s. Oops, that looks kind of weird. F of s minus s times f of 0, right, where f is the function, right, is the solution, minus f prime of 0. Right. And then let's do one more so you can see the pattern. Right. S cubed f of s minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. Right? So basically, you start with s to the power of whatever derivative you have. Right? So if you're taking the nth derivative, then n is 3. The third derivative, then n is 3. You always multiply the Laplace transform by s cubed, or s to whatever n you have, and then you subtract s squared s up till you get to s equals 0. Right? Sorry, s equals 1, or s to the 0. Right? And then you keep increasing the derivatives each term. Right? So it's a pretty simple term or pattern to recognize. Right? So you can just use it like that. Right? Okay. So what is this going to be for us? Well, the Laplace transform of y prime is by definition s times f of s. Right? Or since we're using little y for the function, let's use capital Y for the Laplace transform. So s times y of s, right, minus y of 0, right, that's just the first part, the Laplace transform of y prime, plus 6 times the Laplace transform of y, right, which is just y of s, equals 1 over s minus 4. Now, what is the idea? What are we going to do next? Right? All we did right now is take the Laplace transform of both sides, which we can actually simplify a little bit more. But let's simplify it one more time before I say anything else. So it has s plus 6, big Y of s, minus y of 0, which we're assuming is equal to 2. Right? So y of 0 is 2. And now it's simplified. Okay. Now what's the idea? What we're going to do now is solve for big Y of s. Why? Well, if we solve for big Y of s, then we can take the Laplace inverse of both sides, and we're going to get y, right, by definition. Now, we don't know that there's a unique solution if we were just given an equation like this. However, we do know there is a unique solution by Theorem 1, section 2.4. So that's one way to guarantee that the Laplace inverse of whatever we get is unique. Right? Not only that, we can also say, okay, we get an answer and we take the Laplace inverse, at least one. Well, if whatever function we find satisfies the conditions here, right, or satisfies the conditions for uniqueness, where we were, right, where basically the condition for uniqueness of the Laplace inverse was that your function is continuous. As long as we have that, then we're done. But again, we know our function is continuous by this property here. So we're justified to take the Laplace inverse, and we know that we're guaranteed to get a unique solution, assuming that we know how to compute the Laplace inverse and whatever's on the right-hand side. But this is the idea. This is the process. Take the Laplace inverse of both sides. You get some expression involving s and the Laplace transform of y. So now it's become an algebra problem, because now what you want to do is solve for y of s, right? Big Y of s. So it's an algebra problem. And then you want to take the Laplace inverse, right, using the table that I gave you. And that's the idea. Okay, so let's try that. Let's add 2 to both sides, divide by s plus 6. So what we get is big Y of s equals, so we get 1 over s minus 4, s plus 6, right, plus 2 over s plus 6. Now, we want to take the Laplace inverse of both sides. Right, so let's do that. Right, so the Laplace inverse, actually let me do it like this, which implies y of t is going to be equal to the Laplace inverse of y of s. And again, we know that this is unique because y is continuous by Theorem 1, section 2.4. Right? And this is going to be the Laplace inverse of 1 over s minus 4 times s plus 6. By linearity, right, we can separate the sum and move constants outside. 2 times the plus inverse of 1 over s plus 6. So as long as we can find both of these things, let me underline them. As long as we can find both of these things, we're done. We have what y of t is. I'm going to do that in the next video because we're going to have to do partial fractions, right? So I don't want to keep the video too long, but that's the idea. This is the process.